All right, so let's think a little more about this Richter scale. Magnitude 2, that's a small earthquake, right? Magnitude 2 means 10 squared, which is 100 times mu naught. That is the energy released by a magnitude 2.0 earthquake. Okay, so it is a small earthquake, and you probably wouldn't feel it very much unless it's very, very close, unless the epicenter is very close to where you are. Magnitude 3 means what? 10 to the third, which is 1,000, okay, times mu naught. All right, so the when you say there's an earthquake which measures 3.0 on the Richter scale, what that means is that the energy released by the earthquake was 1,000 times that mu naught, which was that reference number, universally defined. All right, magnitude 4 then means 10 to the fourth. What is that? It's 100. It's 10,000 times mu naught, right? And so that's exactly what those magnitudes mean. Now it is not linear, right? So 10 to the fourth is not twice 10 squared, even though 4 is twice 2. Okay, so again, this is not a linear scale, and in fact, it is exponential because you're talking about 10 squared, 10 cubed, and 10 fourth. But basically, the logarithmic scale goes, and we call this the inverse function of exponential function in mathematics. But what it means is it works the opposite direction. It works sort of the other way as opposed to the exponential. So when the magnitude is 4, notice here, it's 10,000 as opposed to 100. What does it mean? This means this is 100 times more powerful, or 100 times as powerful as this one. How did you get 100 times? Well, it's this minus that, this divided by this, right? And notice here, even the magnitude 4 earthquake compared to magnitude 3 earthquake, this is 10 times as powerful as a 3.0 earthquake. You notice here, every time this number goes up by 1, the scale or the intensity of the earthquake gets multiplied by 10 times. And that's why you go from 10 to the third to 10 to the fourth, it again multiplied by 10 times. 10 times 10 is of course 100 times, right? So each time the scale goes up by 1, very, very careful, very important here. Maybe this is the most important line of this lesson. Each time the scale goes up by 1, the earthquake energy becomes 10 times as big. Right. So you can say, well, what's the difference between a 6.0 and a 7.0? The answer, the 6.0 is 10 times as weak as the 7.0 earthquake. See, that's something that we all should understand, in my opinion. All right, so let's compare some earthquakes. The El Segundo earthquake was a 1.6, a tiny one, okay? And the Castaic one in February of 2020 was a 3.5. All right, let's compare these. What can we compare? This will be like this: 10, 3.5 divided by 10, 1.6. Now, the way it works with this is, and again, I'm not going to go into all the details of mathematics, especially the decimal exponents. But when you divide a number with an exponent by a number with an exponent, if the base number is the same, what you do is you subtract the exponents. All right, so 3.5 minus 1.6 is 1.9. All right, and then you raise 10 to that number because that's what the magnitude means. All right, so when you're comparing a 3.5 earthquake with a 1.6 earthquake, find the difference of these two numbers, which is 1.9, and then raise 10 to that number, which turns out to be about 79.43. Right, so what we are saying is the Castaic earthquake was caused by the energy level, which is about 80 times or 79.43 times as big as the El Segundo earthquake that occurred in October of 2019. Okay, did you get that? All right, so yeah, that's what it means. All right, and so the difference is significant. Okay, the difference is not 1.9, it's 10 to the 1.9. That's the part you have to understand. All right, let's compare the Northridge earthquake 6.7 with the Jamaica, Cuba earthquake of January of 2020, which was a 7.7, right? And by the way, Tohoku had a magnitude of 9.1. This is one of the biggest earthquakes ever recorded in the history of seismology. And of course, it had devastating consequences, including the nuclear meltdown in the nearby nuclear plants. All right, so let's say you have, which one am I comparing this to? Let's compare these two. Let's compare this and this. Okay, so 10 raised to the 7.7 minus 6.7, right? So you take this number and you take this number and you subtract this from that one. That's 1, right? So 1, what does it mean? Well, that means Jamaica, Cuba earthquake had the difference of 1 on the Richter scale, but that means, remember, 10 to the first, which is 10, right? So you can say Jamaica, I should say Jamaica, right? It depends on where you're from, Jamaica or Jamaica. Jamaica, Cuba earthquake was 10 times as big as the Northridge earthquake. And that's kind of surprising because the Northridge earthquake was huge. Okay, I mean, that's the last time COC held classes out there in the parking lot under tents. Okay, that's how serious that place was. I mean, the earthquake was devastating. All right, let's compare the Tohoku with the Northridge. All right, so that would be 9.1 minus 6.7, right? And so that's 2.4. The difference in the Richter scale reading is only 2.4. But remember what you have to do with it. It's 10 to the power of 2.4, not 10 times 2.4. 10 to the power of 2.4. And that turns out to be, you can calculate this on your calculator. All right, so all you have to do is 10, and then you put XY, and then 2.4. That would do. Some of you may have this caret notation on your calculator, but either way, you get a number like 251.2. Okay, and that means the Great Tohoku earthquake that brought a bunch of tsunamis and so on. Tohoku was 251 times as big as the Northridge earthquake. Okay, now that is really surprising, maybe, right? And you would know this unless you understand something of logarithmic scales. Okay, again, I believe it's very important that we all understand how the logarithmic scales work. All right, very quickly. The second application is what you see in 6.3 in the book, and this is the pH level. And this is something you study in chemistry, probably. And I've had students in liberal arts math that worked on like gardens and plants, nurseries, and they were very, and then like pools, you know, gym pools. They're very concerned about pH levels. If you have a goldfish or some sort of fish in a tank at home, you also have to worry about the pH level of the water, because that measures the acidity and the whether it's acid or basic. Basic is sometimes called alkaline, of the liquid. All right, so the pH level measures the concentration of what we call the positive ion called the H plus. Basically, it's a hydrogen ion. That's when the hydrogen atoms, you don't need to know this, by the way, we're in a math class, and I'm a math professor, but when the hydrogen atom loses an electron, it becomes positive. You know, there's an old joke. The hydrogen atom came here and says, hey, I think I lost an electron. And the other person says, are you positive? So yes, I am positive. That's what happens. The hydrogen ion minus the electron is, if you have enough of these, okay, that causes the liquid to be very acid or acidic, right? The concentration is very, very, very low. Okay, that's why it uses the logarithmic scale. So for water, okay, we do have levels of this. For pure water, the concentration of H plus, the hydrogen ion, in a typical water, pure water, is 1 over 10 million. Okay, so that's a very small number, right? 1 to the 10 million. If you write this, 10 million is 10 to the 7th. And if you have 1 over that number, we describe this as 10 to the minus 7. Okay. Again, you don't really know, don't have to know a whole lot of this, but See, this number is always negative, and so some reason chemistry people, maybe they don't like negative numbers. I'm not sure why, but we call this, so take the negative number out, okay? This minus, forget the minus sign. We say that the pH level, which is this number minus the negative sign, is the, so basically the exponent. The pH level is the exponent where you remove that negative sign. So the pure water has the pH level of 7, all right? And the pH level is always between 0 and 14, okay? And the lower it is, the more acidic it is. Because what happens is, like, if you have a pH level of 3, for instance, that's 10 to the third. Do we have a picture of this? It's hard to see this picture, but when the level is like 3, that means it's 10 to the negative third, okay? And that's 1 over 1,000, which is very, very highly concentrated. Even though 1 over 1,000 is not a big number, compared to 1 over 10 million, 1 over 1,000 is a very big number. And so when the pH level is 3, you have something that's very acidic, such as grapefruit juice and tomato juice over here. All right. So the lower the number is, the more acidic the liquid is. Vinegar, for instance, has a pH level of about 2. On the other spectrum is soap water, which has numbers like 12. These things tend to wash off things. Okay, if you have a hand and you know, if you wash your hand with this kind of things here, some of them are actually very dangerous, so you don't want to do that. But if you have soap, okay, with a level of 12, what happens is, if you wash your hands with soap, lots of stuff like bacteria and viruses, they just get washed off of your hand, right? So this is quite useful, but some of these are way dangerous, so you do not want to touch this. Now, our stomach, you know, our bodies are made to function, right? Our stomach has an acid with a level like 1. Okay, this is very strong acid. Why do we have that? Is that bad for you? No, you need this, okay? You need this to digest your food properly. And so your stomach is full of acid, hydrochloric acid, by the way. All right, so other logarithmic scales applications include sound loudness. If you are into like stereo system or something, the loudness is measured in decibels. And so that is also an application of the common logarithm. It's a log-based 10. If you talk about the brightness of stars, which range very widely, the brightness of stars is also measured with the logarithmic scale. So there are all kinds of applications, but the main thing that I wanted to focus on was the Richter scale reading. All right, so make sure you understand how logarithmic scales work, and I have given you some exercises in your homework. All right, so this concludes our discussion on chapter 6. All right, so basically we had exponential growth and the inverse function, which is a logarithmic scale, right? And in the world of science and mathematics, again, this number E, right? This number actually controls a lot of these functions, log and exponential. And this is a number that is used in many scientific applications to describe things that grow and things that decay. So with that, we end chapter 6, and I will see you in chapter 7 again. All right, I'll talk to you later. Have fun. Bye.